Jimenez will tell us about intermittency in imperfect multiplicative cascades.
Okay, good morning. This is something that I've been doing on and off for several years now. I'm interested in how these eddies that you see in turbulence, how they break, or how they become smaller or larger. I mean, you see here, there is this green object that is a fairly large eddy. This happens to be in a channel, but it doesn't matter. I mean, you see it in all flows. And then somehow this object is, you're seeing there something like vorticities, actually, the discriminant. And there are regions in which you choose your threshold right, then you see these large things. And then after a while, they disappear, they are not there. And the question is how. You can do that right, and I frankly don't know how to do it yet. Okay? Or you can do one of these models that people do, starting with Kolmogorov. And okay, this is what I'm going to try to speak today a little. There are two basic cascade models, and this cascade is this process by which you have a hierarchy of things that they keep breaking, and when they break, they change their intensity in some way. Okay, and assume that you're looking, for example, at the velocity difference across a given separation delta x. Okay, the classical Kolmogorov model is that if you know which is the intensity, it's a measure of the intensity, something like the RMS of the velocity separation at some distance, and then you measure the velocity difference at different places, then there will be a more or less universal random variable that relates this intensity to these individual things. Okay, that means, for example, that if you measure the conditional statistics of this quantity given the value of their parent, I mean this is supposed to come from some parent, then you'll see something like that. Okay, all the conditional variables, the conditional variances of this quantity, they are independent of where they come from, and they are just happen to be chosen at random from some pool of intensities. Okay, this gives rise to the regular Kolmogorov 41 cascade. Then this thing was shown not to represent well the experiment, so people invented this multiplicative cascade, which is, this is, if you want the socialist model, this is the feudal or aristocratic model. Okay, you inherit things from your parent. You are breaking down from a stronger parent, then there is still this random variable there, but it applies not to the general intensity of things at that size, but to the intensity of your particular parent. You remember where you come from. And then if you do the same plot like this here, then what happens is if you look at the conditional variance of the quantity as some size, as some separation, as a function of where it is coming from as the intensity of its parent, then you will see something in which the variance is proportional to the intensity of the other parents. Okay, these things are nice because they are guaranteed to be intermittent and, sorry, wrong way around. Okay, okay, and we want things to be intermittent because we know that things are intermittent in turbulence, and it's easy to see that any multiplicative cascade is going to be intermittent, and this happens because one way of measuring intermittency, this is the main purpose of this slide. I'm going to define intermittency from now on in terms of the flatness of the structure function. You have the structure function. The structure function is the mean value of the lambda power of the velocity difference in this case. Okay, and then you can, the structure function by itself doesn't say much because the structure function is a dimensional quantity. But if you normalize it, we say the second order structure function raised to a nice power, then you have something which is the flatness. Okay, and the flatness tells you how important is that the tails with respect to the center. If your high order flatness are large, that means that your tails are high, and the thing is becoming intermittent. And when you have a multiplicative cascade, it's easy to see that the flatness of a given order after n steps of your cascade is the flatness of this multiplier to the nth power. And because you know that the flatness has to be bigger than 1, and this is a theorem, okay, this comes from Chebyshev inequalities, then eventually they will grow, and they will grow without bound. And I will call intermittent anything for which I can show that the flatness grows without bound with a number of steps. Okay? So we have this multiplicative model. Now, of course, it has to be tested. The fact that it gives you something which is intermittent doesn't prove that it's right. Okay? So people have tested it, and the way to test it, or one way to test it, is you take a variable, which is usually not the velocity difference, but this one-dimensional dissipation surrogate or something like that. And this is nice because it's something that has a bound. I mean, it cannot cascade to something which is bigger than itself. Okay? And then you measure this quantity, which is the ratio of the dissipation at a size delta x, compared to the dissipation of the segment that contains the same segment, but which is twice as large. So you start with something like this, and you can do this from experiment. You take a big increment, you take a small increment in the smaller increment in the center, and then you measure the ratio between the dissipation in this smaller integer to the dissipation in this large integer, in that interval, sorry. Okay? And then this is going to give you a random function. And the basic idea of multiplicative cascade is that the PDF of this random number here is independent of the separation at which you are doing this. Okay, it's the same as long as you are in the Inertial-range. The same if you are looking at this scale or that scale or that scale. So you can test that, and it doesn't work. Okay, doesn't work, and I mean, people have tried it, and this is, for example, an old paper by Antonia, in which he plotted these points, which I tell you now what they are, and he said that, well, it is clear that they're constant. Well, they're not constant. I mean, they're not constant. These points are basically, this is the PDF of this multiplier for one particular case, okay, from one case here, and then this is each PDF is for a different separation. The large separations are here. The small separations are there. The cascade will go from here to there. Okay, and then this at a reasonably high Reynolds number. I cannot do this using my DNSs. The Reynolds number is not high enough. So what I did is I got data from these two guys. This is a washing machine of Tavelin. This is some atmospheric boundary layer of Antonia. And actually, this boundary layer was the same one that was used for these plots, okay? Done in some different way. But I mean, somehow, Antonia saw this and thought that it was constant, but they are not constant. I mean, it's clear that they are not constant. They're changing slowly. I mean, you see that the Reynolds number here is high, so that this is a big range, and this changes this maximum here, which is what I'm plotting there, changes from 1.5 to 3 or something like that. It's a factor of 2 over several orders of magnitude, but it's still not constant. There is something that is changing there. The question is why, and whether you can improve a little in this multiplicative model to create something that is more in accordance to this fact that what you're seeing there is not really a multiplicative cascade. And you have to do that with care. I mean, you have the idea that this thing has to be more or less invariant to size, so you cannot just create something that is, you say, okay, this is grows because it grows because this thing is small and this is large. I mean, you have to do that with a little care. So you started thinking a little, and let's go back to this plot, which is the one which I think are better to look at this. These are the two models that I showed you, and let me remind you, what they have here is the conditional variance, or the conditional second-order structure function of quantities measured at a size delta x. What they have here is the magnitude. This is a statistical quantity. This is not. This is the actual magnitude of the velocity difference in the parent interval. Okay, so I have And doing this experiment, I have my long set of data. I break this into segments 1 second long. Then I measure the center half second of each segment. And then for all the segments in which the velocity difference over 1 second is minus 15 or minus 25, then I compute the variance of all the children segment. Okay, so and then if this were Kolmogorov, I mean, then I expect here a variance in which this will be flat. It will be independent of the parent. If this were multiplicative, I will expect to see something like this. Okay, what you see is something in between, as usual. Okay, what you see something like this. This is the standard deviation. This is not the variance, sorry. This is standard deviation. This is square root, okay, of the children. This is the intensity of the parents. Each line here is a different size in the experiment, okay. And then you see things that they look something like this, but they don't go to zero. They clearly don't go to zero, okay. So even when the velocity difference of the parent is zero, the children still can do something, okay? Even if there is the parent is dirt poor, the child still can do something, okay? So can do. And then well, I mean, when I see that, I tend to think that, well, why don't we look at a model that look like this? They have this multiplicative part here, they have this random part there, okay? And this is what I call an imperfect multiplicative cascade. It is still multiplicative because it has this factor there, but it has this noise, this background influence that is here, okay? And that does not depend on the intensity of the parent. It just depends on the general wealth of the previous step, okay? And well, you have to look at this a little more. And the next thing that I try to do is, well, okay, how can you measure this? How can you measure? I mean, what can you say about this? The statistics of this multiplier and the statistics of this noise there, and will that still give you something that is intermittent? Okay. So how do you measure that? Well, the obvious thing is you take the second order structure function, for example, normalize it in some way, okay? And then if you take a process of this type and compute the second order structure function of this, you get something that has to do with the second order structure function of that, the second order structure function of that, something to do with the mean values, and then something that has to do with the second order structure function of the previous step. Okay, so you can do that now, and then you get a parabola. Okay, the straight line that you were seeing before were the square root of that. Okay, you see a parabola, and that parabola has a vertex, and the height of that vertex tells you essentially which is the variance of the noise part of this cascade model, and the curvature tells you which is the variance, which is the second order structure function of the multiplicative part of the cascade. So you get numbers. And the interesting thing here is that these two numbers are roughly of the same order. Okay, that means that the two processes, the inheritance and the noise, are of the same order. This is not that they're not fully different. The thing is not predominantly multiplicative or predominantly regular. It's something in between. And that makes sense, because when you look again at this eddy that I put you at the beginning, okay, this eddy is stronger. That's why I have been able to draw it. I mean, for that reason, this is stronger than the background. So when it breaks down, or when it evolves, it's going to evolve based on its intensity, and that evolution is the thing that is modeled by the multiplicative part of the process. But then it's immersed in this sea of junk, in which there are many other eddies which are pushing it and kicking it around. And this is what is modeled by this noise part of the process. Okay? And basically, you look at the energy equation, this process by which this eddy decays by itself is something that is given by the dissipation. And dissipation is U prime cube over L. Okay? And this process that is the noise coming from outside. This is going to be given by the fluxes coming through the sizes of your box. And this is of the same order. And they have to be of the same order because they have the same dimensions, and in the inertial range there is only one thing that you can do with the dimensions, but they are of the same order. And because this dissipation is of the same order as the flux that is hitting you from the sizes, then that means that this thing has to be of the same order as that, and that's what you get from the experiment. So let me analyze now this model a little to see whether it will still be intermittent or not. This is the model. Okay, these primes here are the RMS value. Okay, so it was basically the model that was put in there. So let me normalize things. Instead of this V now is going to be anything that is going to cascade. In the sample that I've given you, these were the velocity difference. Okay, so now I define a normalized velocity difference, which is d divided by its standard deviation. So the standard deviation of these things are always going to be 1. And then when you try to write the equation for these W's, then you find out that what you want to have here are not these two random processes, but something which is some scale version of those random processes, which is going to be each random process is normalized not by its variance, not by its standard deviation, but by something which is a mixture of the two standard standard deviations of the two. And it has a set of properties. The important one from our point of view is that the second order structure function, these sigmas are going to be the second order structure functions of these multipliers here, okay, the two random processes. The two second order structure functions sum to 1, and that means that each of them is smaller than 1. Okay? So when you start at the level of second order structure function, each of them is going to be smaller than 1. And then you can choose this to be 0, and that just centers the value of delta 1 of omega. Okay. So the question, are they intermittent? As I told you in the second slide, what I mean for that is whether the flatness of the B's grow without bound after many steps. And the flatness of the B's are actually the structure functions of the W's. Okay, so we want to see how the structure functions of the W's change with the cascade step. And then we just write the relation between the structure function in step k plus 1 and the structure function in step k. And they form a well-ordered system in which you can do everything at one order based only on the smaller orders. Okay, so that means that you can write this in terms of a matrix, which is lower diagonal, and this is the thing that has this is the multiplicative part of the process, and this is the additive part of the process. And what you have here are moments of the two random processes. Okay, and you write this as a matrix. Realize that you can diagonalize this matrix. Is lower triangular, so the eigenvalues are these leading elements in the diagonal, and these leading elements are the moments of the multiplier of the two processes, the multiplier and the node. This is the moments of the multiplier. Okay, and then there is a set of eigenvectors, which is also lower diagonal, lower triangular. Okay, so you put this into the system of eigenvectors, and that means that you create now something that is not going to be the structure function, the flatnesses, but something which is a linear combination of the flatnesses, but you can invert that later. Okay, and then you get now an equation that looks like this, which has the advantage of being moving diagonal, so that for each order you have a single equation that doesn't see the other orders. Okay, and then this looks like here you have this linear combination of a structure function at a given time in the cascade. Here you have the previous time. Here you have the moment of the multiplier, and here you have something that is related to the moment of the noises. Okay? So you solve this. This is trivial. You write the solution. It looks like that. And then the question of whether this will grow with time or not, this will grow with the cascade step or not, depends on whether this thing is bigger than 1 or this thing is smaller than 1. Okay? If the structure function, the lambda moment of the multiplier is bigger than 1, then this thing will grow, and then the process will be intermittent. If it is smaller than 1, that process will be regular. Okay? And typically, these things grow with the order, grow with lambda. So what happens is that you start with something that is regular, and it's always regular because remember that the second order moment was smaller than 1. That's what I told you was important. So it will always be regular. Then at some point, probably, the multiplier starts having moments that are bigger than 1, and then all the moments on top of that will be intermittent. Okay? And this is true. These were not the flatnesses. It was this linear combination of the flatnesses. But now you can invert this. You can invert this by multiplying it by the eigenvectors. And because the eigenvectors were also lower triangular, that means that if you want to compute the flatness at order lambda, you only have to worry about these t's of order less than lambda. So if you are here, and all these t's here are regular, all your flatness here are regular, and there is nothing that's intermittent. And as soon as you move into this, then you start getting things which are intermittent. This is slightly different from the normal multiplicative cascade, in which everything here will be anomalous. Okay, here only part of the orders are anomalous. So now the question is, how do you measure these values, the sigmas, the moments of the multiplier and of the additive constant? Then you play the same game that I was playing for the second order structure function. You plot the conditional structure function of the child as a function of the intensity of the parent. Okay, for different orders, for different structure functions, and you get something which is look like a parabola, look like a cubic, look like a fourth order. And the coefficients, you do a best fit in there, and those best fits are quite good. You see that there are several separations here, okay? And that's why you see them, I mean, there are several lines in there. And these dots are the fits, so the fits are reasonably good. Okay? And then from there you get moments, and you get the important ones are these blue ones, and these blue ones are the moments of the multiplier. Okay, and the moments of the multiplier start being less than 1, and then in this particular case, the first time in which I can believe that this thing is going to be of the order of 1, and this thing is beginning to be intermittent, is in the 6th order structure function. Okay? Now I have to warn you, I have put here these error bars, and these error bars come from the difference between different separations here. Almost any other way of putting error bars will be larger. So these are somewhere in there, but I'm not terribly sure. Certainly beyond these are science fiction. Here you can see, for example, the error bar of some of these moment of the additive constant that is somewhere in there, and the error bar is already huge. Okay, but it does look like for the low moment, this thing is going to be regular, and then it's not. And I don't know whether this is true or not, but it's something that in principle can be checked by looking at the scaling exponents of the structure functions, and these people have measured that a lot, and I have put here several of the standard compilation of data, which are these symbols there, okay? And this will be Kolmogorov 41, okay? And the data are there. Any multiplicative cascade will look like this black line there. It will be below Kolmogorov here. It will cross 1 as 3, it has to. And then it will probably go below or above. I mean, it will not, it will only follow Kolmogorov 41 here, okay? While these imperfect processes will follow Kolmogorov 41 strictly for a while and then start to diverge. So this is basically what I have to say. So let me summarize. The first thing is that the breakdown coefficients of the dissipation, which is the thing for which the experiments have been published, they vary with the separation. That PDF is not universal, and I think that is clearly not universal. It becomes wider as you start getting into smaller and smaller, separations. Okay, and it seems to, when you look at the data, it seems to have a trend to become wider as the Reynolds number becomes bigger, but that is not clear. If you want to model this cascade in terms of one of these simple models or shell models almost, I think that that model better, I mean not much better, but better, by a mixed process in which you have both a multiplicative part and an additive part. And they are both of the same order. I mean, when you look at the experiment, they are both of the same order, and they should be. And if this is true, that means that the low orders should be regular and should be really regular, and only the higher order moments starting somewhere. What I get from the data that I have, which are not very good, okay? If around 6 or something like that, 4 or 6, only starting there, the thing will be intermittent. Thank you.
Must be some questions and comments.
Bob Antonio's not often wrong, so do you think it's just the question that he couldn't measure those things accurately enough? He didn't show error bars on that.
I don't see anything wrong with his measurements. His measurements are these. His measurements are those pointing there. I don't know why. I mean, I always read that paper and I said, well, how is he saying that this is constant? This is not constant. The thing is I mean, there is some, there is this, I mean, this is basically Kolmogorov 62. This paper was in the 70s. So I think that he just didn't want to go against big Kolmogorov. I mean, clearly his measurements are consistent with everything else.
First, Roberto.
Yeah, I have a comment and a question.
Okay.
The comment is that if you take into account the scaling property of the Navier-Stokes equation, multiplicative process cannot be strictly true because of the scaling variance in time, which means that the variables must be not independent. In other words, that at each step you have a dependence of the probability distribution from the previous one.
Yeah.
Now, if this is true, if you make measurements like that, I mean, it's slightly unfair to compare this with the multiplicative process.
Well, first, the multiplicative process assumes independence, so if I can't compare. I mean, the strict multiplicative, the self-similar multiplicative process assumes
in the simplest case.
Yeah, in the simplest case. So, okay, yes. I mean, if you say that the self-similar multiplicative process has neat corrections, yes, so that's what I'm doing. I mean, I'm not saying that is, I mean, that the whole thing is wrong. So now you had a question. Is this a question or is?
Well, the question is that if you take into account the scale invariance in time, then probably you will end up with a different model in which you don't need this background.
Actually, no, I did not. I mean, I tried that. I tried many things. I mean, a lot of this was done in the last program here at the Newton Institute. And I spent like a couple of months a month actually, with traveling, trying to do all things on the possible correlation, the correlation between different sizes and the correlation between different multipliers. They're in there, but this is an order 1 effect. I mean, all these are small corrections that you can fix it, but this is an order 1 effect. If you look at this, where things are scaled correctly, if you look at these structure functions, in which the blue are the variance. I mean, in this case too, the blue is the variance of the multiplier, and the red is the variance of the noise. They are the same, basically. They are both 0.5. I mean, it's half and half. And they have to be. I mean, you look at, you take a cube of fluid, and then you look at how much energy is being dissipated from one scale to another, and how much energy is coming from the sizes. They are the same order. They have to be the same order, and they are.
Allow one last quick question by screen, please.
Picking a peak is a very sensitive measure of, for instance, just take these distributions. No, just go back the one you had.
Yeah, picking a peak of that.
No, not that.
Yeah,
just
no,
go back
to
to the one you had.
It's a peak of that.
No, I know, but I'm telling you that picking a peak is a very sensitive measure of whether the distributions collapse or not. So even if you pick the peak, you go to the right-hand diagram here. For delta x below about few hundred or so, it is surely the distribution is evolving. Everybody who made any measurements like that knew. But later on, if you go to a few hundred or so delta x by eta and beyond, then it was not very sensitive. The distribution was not very sensitive to delta x. And in fact, that's what Bob Antonio's measurements, or the numbers you have there, seem to suggest. You see, initially it's going up, of course, as it should. Thereafter, it is actually not changing all that much. In fact, I suggest that instead of picking the peak, you pick some moment of it, which
I did.
Telling you.
I did, but I mean,
telling you
here. I mean, anything that I look between these
you
and
did.
that.
I don't
Yeah,
know what
I mean,
you
they're
did.
different.
But you should show them if you
Eh?
did. But the basic point is that there is a range of scales for which it is sensitively dependent on the levels, as you actually quite rightly point out. But beyond that, it is not so sensitively changing, and that is the essence of the.
The only place in Antonia that I can see which
approximation.
are independent of the level are those 2 points.
One has to
Those-
put error bars on those, and use.
I cannot put error bars on that. I can put error bars in this, okay? I can put
Whatever,
error bars in
yeah.
those because those are taken from his paper. These are taken from your
But
paper.
that's the general idea, anyhow.
Those
Beyond a few hundred in delta x.
those Srini are taken from these are yours. This is taken from your paper.
Yeah, okay.
Okay.
Fine. This.
To me, that is also fine.
My point is, picking a peak is not such a great idea, and in fact, you have seen my graphs. There is a small sensitivity, small dependence on delta x, but not really all that much. That's what I would say from there.
This,
That's what I would say.
that.
But I
Which is-
agree
which
that
is
there may be an effect of.
Consistent with all the others.
I agree. I do agree that there may be an effect. Okay.
This is